At the heart of our understanding of electricity and magnetism lies a deceptively simple question. What exactly is magnetism, and where does it come from? For centuries, humans observed that certain materials, like lodestones, had the mysterious ability to attract iron, to twist needles, and to guide travelers across seas and continents. This strange force was separate from the known forces of nature, acting at a distance without visible contact. But as the 19th century progressed, a growing number of experiments began to hint that magnetism was not an isolated phenomenon. It was connected, intimately, to the behavior of electric charges. Before the era of precise measurements and controlled laboratory experiments, electricity was largely understood in terms of static charges, sparks, and simple conduction. People knew that rubbing amber could attract small bits of paper, and that lightning was a dramatic display of electric energy. Magnetism, on the other hand, seemed inherent to specific minerals, inexplicable and mysterious. It was in this intellectual climate that the revolutionary idea emerged. Perhaps magnetism was not an inherent property of certain materials alone, but a result of motion, a dynamic effect rather than a static one. It was Henry Augustus Rowland, an American physicist, who would provide some of the clearest evidence of this connection. Rowland's insight built upon earlier theoretical work, which suggested that moving charges might produce effects that stationary charges could not. The notion was radical, for it implied that a simple movement of tiny particles, electric charges, could generate a magnetic field, a phenomenon that until then had seemed tied to certain solid objects like iron. This concept was elegant in its simplicity, yet profound in its implications. It meant that magnetism could be created anywhere there was motion of charge, linking electricity and magnetism into a unified phenomenon. Rowland approached this problem with meticulous care. Unlike modern physicists, he did not have access to digital sensors or precise electronic amplifiers. Instead, he relied on ingenious mechanical setups and painstaking measurement techniques. His central apparatus consisted of metal discs that could be electrically charged and rotated at controlled speeds. By spinning these discs, he created currents moving charges along defined paths, and then measured the resulting magnetic effects. Every movement, every rotation had to be carefully monitored, for the magnetic fields generated were faint, delicate, and easily disturbed by external factors. The laboratory was a stage of precision and patience, where even slight vibrations or temperature changes could affect the results. The brilliance of Rowland's experiment lay not only in its ingenuity, but also in the clarity of its conclusions. As the charged discs rotated, they produced magnetic fields exactly as predicted by theory. The faster the discs spun, the stronger the magnetic effect. The configuration of the fields corresponded precisely to the geometry of the moving charges. Through careful repetition and verification, Rowland established beyond doubt that moving electric charges were indeed capable of generating magnetism. This was a watershed moment in physics. It transformed magnetism from a mysterious, almost mystical force into a quantifiable, observable consequence of electric motion. But the significance of this discovery extends far beyond the laboratory measurements. It fundamentally reshaped the way scientists understood the natural world. Prior to Rowland, electricity and magnetism were treated as largely independent phenomena. Sparks could jump across air gaps, magnets could attract iron, and the two were studied separately. Rowland's work revealed a hidden unity, a deep connection between electric charge in motion and magnetic force. It suggested that the forces of nature were not a series of isolated effects, but could be explained through fundamental principles that interconnected seemingly disparate phenomena. This understanding opened the door to a new era of theoretical and practical exploration. Scientists began to see that moving charges in wires could produce magnetic fields, and conversely, that changing magnetic fields could induce electrical currents. These principles would eventually lead to the development of electric motors, generators, and the entire field of electromagnetism. Rowland's experiment was a cornerstone in this edifice of knowledge, a clear demonstration that motion is not merely a passive property of particles, but an active agent in the creation of force fields. Rowland's methodology also highlighted an important philosophical lesson in science. While theory can suggest possibilities, it is through careful experiment that nature's truths are confirmed. Rowland did not merely accept the theoretical prediction that moving charges could produce magnetism. He tested it under controlled conditions, measured it with precision, and documented it with clarity. His work serves as a reminder that scientific discovery is not only about brilliant ideas, but about rigorous, meticulous inquiry, the patience to repeat experiments, and the attention to subtle details that might otherwise be overlooked. Moreover, the implications of this discovery extend to the microscopic level. While Rowland worked with macroscopic rotating disks, the underlying principle applies to electrons, ions, and fundamental particles. Every moving electron in every atom generates a magnetic field. The collective motion of countless electrons gives rise to the magnetism observed in everyday materials. Understanding this connection allows physicists to manipulate magnetic properties, design new materials, and even probe the structure of matter itself. In essence, Rowland's findings provided a bridge between the tangible laboratory measurements of his time and the invisible, subatomic world that would later be explored with advanced instruments. Even the broader cultural and technological impact of this discovery is profound. By showing that magnetism could be generated by moving charges, Rowland helped lay the foundation for the modern electrical age. The electric motor, which powers countless machines from household appliances to industrial equipment, relies on precisely the principle he demonstrated. Magnetic storage, transformers, and even modern communication systems trace their origins to this basic insight. Rowland's work illustrates a recurring pattern in the history of science. A seemingly abstract laboratory experiment can eventually lead to technologies that transform society. The beauty of Rowland's experiment lies also in its simplicity. At its core, it involves nothing more than a charged disk, rotation, and careful measurement. Yet this simplicity masks a profound truth about the universe. It reminds us that fundamental laws often manifest in subtle ways, waiting to be uncovered by careful observation. The motion of particles, invisible to the naked eye, can create forces that shape the macroscopic world, guiding compasses, powering devices, and structuring the behavior of matter. This duality between the microscopic and the macroscopic, the hidden and the observable, is a recurring theme in physics, and Rowland's work exemplifies it beautifully. In addition, the experiment emphasizes the importance of experimental verification in scientific progress. Theoretical predictions, no matter how elegant, require confirmation. Rowland's meticulous approach, controlling variables, repeating measurements, and ensuring accuracy, embodies the scientific method. It is a lesson that transcends this particular discovery, applying to all areas of inquiry. True understanding arises from the interplay between theory and experiment, prediction and observation. As we reflect on the impact of Rowland's work, it becomes clear that the discovery of the magnetic effects of moving charges is not merely a technical detail in physics. It represents a conceptual shift, a moment when the boundaries between electric and magnetic phenomena dissolved, revealing a unified framework for understanding forces. This insight paved the way for the later formulation of Maxwell's equations, which elegantly describe how electric and magnetic fields interact, propagate, and give rise to electromagnetic waves. Rowland's contribution, though often overshadowed by the more famous theoretical work, was crucial in providing tangible, experimental proof of a concept that would revolutionize physics. Finally, the human aspect of this discovery should not be overlooked. Rowland's work exemplifies curiosity, perseverance, and intellectual courage. To challenge established notions, to pursue careful measurements in the face of skepticism, and to draw profound conclusions from careful observation requires a rare combination of intellect and dedication. His experiment stands as a testament not only to the laws of nature, but to the spirit of scientific inquiry itself. In conclusion, the discovery that moving electric charges generate magnetic fields represents a pivotal moment in the history of physics. It transformed magnetism from a mysterious, almost mystical phenomenon into a predictable, measurable consequence of motion. Rowland's experiments demonstrated this connection with precision, elegance, and clarity, providing a foundation for the understanding of electromagnetism that underpins modern technology and scientific thought. By revealing the hidden dynamism of electric charges, Rowland opened a window onto a universe governed by unified principles, where motion and force, electricity and magnetism are intertwined in an intricate and beautiful dance. This insight continues to inspire scientists, engineers, and curious minds, reminding us that the smallest motions can give rise to forces that shape our world in profound ways. The power of scientific discovery often lies as much in the way an experiment is conducted as in the conclusions it draws. In the case of Henry Augustus Rowland, his experimental setup to investigate the magnetic effects of moving electric charges was a masterpiece of ingenuity, precision, and careful observation. Unlike modern laboratories equipped with digital sensors, automated controllers, and highly sensitive electronics, Rowland worked in an era where experimental skill, meticulous planning, and physical intuition were paramount. Every aspect of his apparatus reflected an understanding not just of the laws he wished to explore, but of the practical challenges that could obscure those laws if left unaddressed. At the center of Rowland's approach was the recognition that moving charges, whether in wires, disks, or other conductive materials, produced only subtle magnetic effects. These effects were easily swamped by environmental noise, stray magnetic fields, or imperfections in the materials themselves. To measure them, he had to create a system where the motion of charge could be controlled precisely, and where the resulting magnetic fields could be detected with maximum sensitivity. The solution he devised was elegant in its simplicity and profound in its implications. A spinning conductive disk, electrically charged, whose rotation could be carefully adjusted and whose magnetic influence could be measured in a reproducible manner. The disks themselves were no ordinary metal. They had to be carefully fabricated to ensure uniformity, so that the distribution of charge remained consistent as the disk rotated. Any irregularity in shape or density could lead to variations in charge distribution, producing misleading or inconsistent results. Rowland's meticulous attention to these physical details reflects a deep understanding that the precision of an experiment depends not only on theory, but on the exactitude of its materials and the care with which they are handled. The disk was mounted on a spindle capable of rotating smoothly at controlled speeds, allowing Rowland to vary the motion of the charges systematically. By controlling the angular velocity of the disk, he could examine how the speed of moving charge affected the strength of the resulting magnetic field. Generating the electric charge itself required equal care. Rowland used methods available in his time to impart a static electric charge onto the surface of the disk. This was not as simple as placing a charge on the disk. He had to ensure that the charge was distributed evenly and remained stable throughout the rotation. Any leakage of charge or uneven accumulation could distort the measurements. Rowland's approach often involved carefully applied conductors and insulating supports, techniques designed to maintain the purity of the charge distribution and isolate the system from external influences. His understanding of these practical challenges demonstrates an early recognition of a principle that remains crucial in experimental physics today, that the system being studied must be isolated from confounding factors in order for measurements to be meaningful. Once the disk was charged and set in motion, the next challenge was detection. The magnetic fields generated by moving charges, while theoretically predicted, were extraordinarily weak in comparison to natural magnetism present in the environment. Rowland needed a way to detect these subtle forces, to distinguish them from the background noise of the laboratory and the Earth itself. He employed sensitive magnetic needles, carefully shielded and balanced, as his primary instruments. The needles could respond to the tiny magnetic fields produced by the rotating charges, moving in proportion to the strength of the field. However, even these needles required careful calibration and protection from extraneous influences, as stray iron objects, vibrations, or air currents could introduce errors. Rowland's experimental method was iterative and systematic. He did not rely on a single measurement to draw conclusions. Instead, he repeated observations multiple times, varying the speed of rotation, the amount of charge, and the distance between the disk and the detection instruments. By analyzing the patterns that emerged across these multiple trials, he could identify consistent effects and rule out anomalies. This repetition was critical, for it transformed what might have been a series of anecdotal observations into solid, reproducible evidence. In doing so, Rowland exemplified the scientific ideal of verification through careful, methodical experimentation. One of the most striking aspects of Rowland's method was his attention to geometry. He understood that the shape of the disk, the path of the moving charges, and the positioning of the detectors all influenced the results. The magnetic field produced by a moving charge depends on the direction and configuration of its motion relative to the point of measurement. By systematically adjusting the placement of the detecting needles and observing changes in their response, Rowland could map the spatial structure of the magnetic fields generated. This not only confirmed the theoretical predictions, but also provided visual and measurable evidence that moving charges produce fields consistent with the laws of electromagnetism. In addition to the physical setup, Rowland's approach demonstrates the importance of combining theoretical understanding with experimental design. He did not experiment blindly. He used predictions from contemporary theory to guide the construction of his apparatus and the interpretation of his measurements. The theoretical expectation was that a moving charge would produce a magnetic field whose strength depended on the amount of charge and the velocity of its motion. Rowland's experiments were designed specifically to test this hypothesis, and the results consistently confirmed the theory. This interplay between theory and experiment is a hallmark of successful scientific investigation, showing how careful design can transform abstract ideas into observable phenomena. Rowland's work also reflects a broader principle of physics, that simplicity and control are often more powerful than complexity. Rather than attempting to study magnetic effects in messy, real-world systems with countless interacting charges, he constructed a clean, controlled scenario in which variables could be isolated. The spinning disk allowed him to vary one factor at a time: charge, velocity, or geometry, while keeping others constant. This careful control is why his measurements were so convincing, and why they could serve as a foundation for later developments in electromagnetism. Beyond the technical aspects, the experimental setup reveals something profound about the nature of scientific observation. Rowland had to make invisible effects visible. The motion of charges is imperceptible to the human eye, and the magnetic fields they produce are subtle. Yet by devising an apparatus that could amplify and measure these effects, he made the invisible tangible. This transformation, turning theoretical predictions into observable, measurable reality, is one of the core achievements of experimental physics. Rowland's method demonstrates that scientific insight is not only about understanding principles, but also about creating the tools and techniques to witness those principles in action. The meticulous nature of Rowland's experimental design also had practical consequences. By carefully isolating variables and measuring fields precisely, he provided data that could be replicated and verified by others. This reproducibility is a cornerstone of scientific credibility. Modern physics relies heavily on experiments that can be repeated independently, and Rowland's work exemplifies this principle. By documenting his methods and controlling conditions so carefully, he ensured that his findings were not anecdotal or incidental, but solid evidence that could support broader theoretical frameworks. It is also worth noting that the experimental setup required a deep understanding of both electrical and mechanical principles. The spinning disk, the conductors, the insulation, and the detectors all had to function harmoniously. A misalignment in the disk, an uneven charge distribution, or a poorly calibrated needle could undermine the experiment. Rowland's ability to integrate knowledge from different areas, mechanics, electricity, magnetism, demonstrates the interdisciplinary skill required of physicists even in the 19th century. His apparatus was not merely a collection of parts, but a carefully orchestrated system, designed to reveal subtle truths about the natural world. Rowland's methodology teaches another valuable lesson, that careful experimentation often requires patience and attention to detail. The small magnetic fields he measured could easily be overwhelmed by environmental noise or minor imperfections. It took time, persistence, and careful observation to separate the genuine effects from artifacts and background influences. This patience, combined with creativity in designing apparatus, allowed Rowland to make observations that would otherwise have been impossible. In essence, Rowland's experimental setup and method exemplify the intersection of theory, ingenuity, and practical skill. By constructing a controlled system in which moving charges could be precisely manipulated and their magnetic effects observed, he provided the first clear, reproducible evidence of a fundamental principle, that motion of electric charge produces magnetism. His approach combines elegance and rigor, demonstrating that scientific discovery is as much about asking the right questions and creating the right conditions as it is about observing the results. Rowland's work remains a model for experimental design. It shows that even in an era without modern technology, careful thought, mechanical skill, and theoretical insight can produce measurements of remarkable accuracy and significance. His method reminds us that the progress of science depends not only on brilliant ideas, but also on the ability to transform those ideas into observable reality through ingenuity, precision, and relentless attention to detail. The significance of Rowland's findings cannot be overstated, for they mark a turning point in the history of physics, where the mysterious phenomena of electricity and magnetism began to reveal themselves as interconnected aspects of a single underlying reality. Prior to Rowland's experiments, electricity and magnetism were largely studied in isolation. Electrical phenomena were observed in the form of static charges, sparks, and currents in simple circuits, while magnetism seemed bound to specific materials such as lodestones or iron filings. The forces were familiar, yet their relationship remained elusive, a puzzle that had intrigued and confounded generations of natural philosophers. Rowland's work provided concrete, reproducible evidence that moving electric charges create magnetic fields, demonstrating the intimate link between electricity and magnetism. This discovery was more than an incremental addition to scientific knowledge. It represented a conceptual leap. By showing that the motion of charge could generate magnetic effects, Rowland revealed that magnetism is not an intrinsic property of matter alone, but a dynamic phenomenon arising from the movement of charged particles. This insight transformed the way physicists understood the natural world, moving them from a fragmented view of forces to a more unified, coherent understanding of electromagnetism. The implications of this unification were profound for both theory and application. In theoretical terms, Rowland's findings provided critical experimental support for the growing body of work in electromagnetic theory, most notably for the equations later formalized by James Clerk Maxwell. Maxwell's equations describe how electric and magnetic fields interact, propagate, and give rise to electromagnetic waves. The observation that moving charges produce magnetic fields was a fundamental piece of the puzzle, providing the experimental verification needed to give the theory a firm foundation. Rowland's measurements were among the first to quantify this effect with precision, demonstrating that theory and experiment could converge to reveal the underlying laws of nature. The broader significance of Rowland's work is also evident in the conceptual shift it prompted. By demonstrating the connection between charge motion and magnetism, he helped establish the principle that forces in nature could often be understood as arising from fundamental interactions rather than being inherent, isolated phenomena. Magnetism was no longer a mysterious, almost magical force, confined to specific materials. It was a natural consequence of the behavior of charges in motion. This realization encouraged physicists to think in terms of fields and interactions, rather than merely observing forces acting at a distance. The idea that motion and interaction could generate observable effects opened the door to a more sophisticated understanding of the electromagnetic field, a concept that would become central to modern physics. The significance of Rowland's findings extends into the practical realm as well. Understanding that moving charges generate magnetic fields allowed scientists and engineers to design systems that harness this relationship for useful purposes. Electric motors, for example, operate on the principle that currents in coils of wire create magnetic fields, which in turn interact with permanent magnets to produce rotational motion. Generators operate on the reverse principle, converting mechanical motion into electric current through the interaction of moving charges and magnetic fields. The principles demonstrated by Rowland's experiments form the basis for these technologies, which have become integral to modern life. Without the insight that moving charges produce magnetism, the development of these technologies would have been significantly delayed, and the modern electrical world we take for granted might have evolved along a very different timeline. Beyond practical applications, the significance of Rowland's work lies in its ability to illuminate the underlying unity of physical laws. The discovery that moving charges produce magnetic fields provides a concrete example of a principle that recurs throughout physics, that seemingly separate phenomena can often be explained as manifestations of the same underlying processes. Just as Newtonian mechanics revealed the unity of celestial and terrestrial motion, Rowland's work helped reveal the unity of electric and magnetic phenomena. This unifying perspective has profound implications for scientific thought, encouraging researchers to look for connections, patterns, and underlying principles rather than treating phenomena as disconnected curiosities. Rowland's findings also played a crucial role in shaping subsequent research in electromagnetism. By providing clear experimental evidence of the magnetic effects of moving charges, he offered a benchmark against which future experiments could be measured. Subsequent scientists were able to build upon his work, refining measurement techniques, exploring the limits of magnetic effects, and applying the principles to increasingly complex systems. The experimental foundation laid by Rowland thus served as a springboard for deeper exploration, enabling the rapid development of electromagnetic theory in the late 19th and early 20th centuries. In addition to advancing theoretical understanding, Rowland's work had significant educational and conceptual value. His experiments provided a clear, tangible demonstration of abstract principles, making the relationship between electricity and magnetism accessible to students and researchers alike. The ability to observe magnetic effects produced by moving charges helped demystify the forces, showing that they are not arbitrary or mysterious but predictable and measurable. This educational aspect reinforced the growing understanding of electromagnetism as a coherent, unified field, providing a framework for teaching and learning that continues to influence physics education to this day. Rowland's findings also highlight the interplay between precision, innovation, and insight in scientific discovery. The subtle magnetic effects he measured required careful design, meticulous control of variables, and a deep understanding of both theoretical and practical considerations. By creating an experimental setup capable of revealing these delicate phenomena, he demonstrated that scientific progress often depends as much on ingenuity and skill as on conceptual brilliance. The significance of his work, therefore, extends beyond the specific findings themselves. It exemplifies a broader principle about how careful experimentation can uncover fundamental truths about the natural world. Moreover, the findings provide a bridge between macroscopic and microscopic understanding. While Rowland's experiments involved macroscopic disks and observable magnetic effects, the underlying principle applies at the atomic and subatomic level. Every moving electron produces a magnetic field, and the collective motion of electrons in materials gives rise to the magnetism observed in magnets, electronic devices, and magnetic storage systems. By establishing the principle in a controlled experimental setting, Rowland laid the groundwork for later investigations into atomics, scale magnetism, spin dynamics, and quantum mechanical effects. In this sense, his work is both historically significant and foundational for ongoing research in modern physics. The significance of Rowland's work can also be appreciated in terms of its role in shaping the conceptual framework of electromagnetism. By demonstrating the direct link between moving charges and magnetic fields, he helped solidify the notion of fields as a central concept in physics. Magnetic fields, like electric fields, could now be understood as real entities generated by physical processes rather than abstract mathematical constructs. This conceptual clarity enabled subsequent theorists to develop more comprehensive models of electromagnetic interactions, culminating in the elegant synthesis of Maxwell's equations and the later development of electromagnetic wave theory. Rowland's experiments also underscore the importance of experimental verification in establishing scientific truth. Theoretical predictions, no matter how elegant or plausible, require empirical confirmation. Rowland's careful measurements provided that confirmation, transforming the theoretical expectation that moving charges produce magnetism into an observable reality. This validation is a cornerstone of scientific methodology, illustrating the interplay between theory and experiment that drives the advancement of knowledge. Without such verification, the connection between electricity and magnetism might have remained speculative, delaying the development of technologies and the refinement of theoretical frameworks. Finally, the significance of Rowland's findings lies in their enduring influence. The principle that moving charges generate magnetic fields remains central to countless technologies, from electric motors and generators to magnetic resonance imaging, particle accelerators, and data storage systems. It is a foundational concept that continues to inform research, education, and technological innovation. The experimental methods he developed and the precision with which he measured the magnetic effects of moving charges set a standard for future generations of physicists, emphasizing the importance of careful design, meticulous measurement, and critical analysis in the pursuit of understanding. In sum, the significance of Rowland's findings is multifaceted. They transformed the understanding of magnetism from a mysterious, material, bound phenomenon into a dynamic effect arising from moving charges. They provided essential experimental support for the development of electromagnetic theory and Maxwell's equations. They influenced the design and operation of countless technologies that underpin modern society. They clarified conceptual frameworks, bridging macroscopic observation and microscopic understanding. They exemplified the power of careful experimentation and precise measurement, and they continue to inspire scientific inquiry, education, and technological innovation more than a century later. The discovery that moving charges create magnetism is not just an experimental result. It is a pivotal insight into the unity of physical laws, the nature of forces, and the intricate connections that govern the behavior of the universe. The relationship between electric current, moving charges, and magnetism is a cornerstone of our understanding of electromagnetism, a connection that was illuminated with remarkable clarity through the work of Henry Augustus Rowland. To appreciate this connection, it is essential to understand the nature of electric current itself. Electric current is, at its most fundamental level, the flow of electric charge. In metals, these charges are primarily electrons, microscopic particles whose motion underlies the phenomena we observe as electrical activity. While static charges produce electric fields, it is the motion of these charges that gives rise to a magnetic effect, a subtle but profound realization that reshaped the landscape of physics. The concept that moving charges produce magnetism was radical in its time because it required a shift in perspective. For centuries, magnetism had been associated with particular materials, especially iron, cobalt, and nickel, whose behavior seemed intrinsic and inexplicable. Electricity, by contrast, had been studied largely in static form: accumulated charges on objects, sparks, and simple conduction. Rowland's insight, building upon earlier theoretical and experimental work, demonstrated that magnetism is not confined to specific materials, but arises naturally whenever charges move. This insight revealed that the seemingly separate forces of electricity and magnetism were intimately connected, two sides of the same coin, observable through the motion of charged particles. The link between current and magnetism can be understood in practical terms through the behavior of a simple conductor. When an electric current passes through a wire, electrons move along the conductor. This motion, invisible to the eye and imperceptible without sensitive instruments, generates a magnetic field surrounding the wire. The orientation and strength of this field depend on the direction and magnitude of the current. Rowland's experiments, while employing rotating disks rather than linear wires, exemplified the same principle. The movement of charges in a controlled path produces measurable magnetic effects, confirming that current and moving charges are intrinsically linked to magnetism. Rowland's work extended beyond the simple observation of magnetic effects. He was able to quantify the relationship, demonstrating that the strength of the magnetic field increases with the speed of the moving charge and the amount of charge in motion. This quantitative understanding is critical because it provides a predictable, repeatable connection between electric current and magnetism. In essence, it allows physicists and engineers to calculate the magnetic influence of a given current, a capability that forms the basis for designing electric motors, generators, transformers, and countless other devices that rely on precise manipulation of electromagnetic forces. The experiments highlight a fundamental principle. Magnetism is not a mysterious force, but a consequence of the movement of electric charges. This principle can be extended to a wide variety of systems. In atomic and molecular structures, electrons move in orbits or along specific paths, generating tiny magnetic fields. In bulk materials, the collective motion of countless electrons produces macroscopic magnetism, as seen in permanent magnets. Rowland's work made it possible to understand these phenomena in a coherent framework, linking the motion of individual charges to observable magnetic effects in larger systems. Electric currents, whether in a laboratory disk, a household wire, or the human nervous system, create magnetic fields that interact with their environment. Rowland's experiments were critical in demonstrating this interaction in a controlled setting, where the variables could be carefully monitored. The precision of his setup allowed him to show that the magnetic field is oriented perpendicular to the direction of charge movement, a relationship that later became formalized in the right-hand rule, a simple yet powerful way of predicting the direction of magnetic fields around currents. This directional relationship underscores the predictable nature of the connection between moving charges and magnetism, and highlights the elegance of the physical laws that govern these phenomena. Understanding this connection also provides insight into why electrical devices function as they do. Electric motors, for instance, rely on the magnetic fields generated by current, carrying wires to produce rotational motion. The torque that drives the motor arises from the interaction between the magnetic field of the moving charges in the wire and the magnetic field of the permanent magnets or other coils within the motor. Rowland's experiments laid the experimental groundwork for this understanding by showing that the motion of charges produces fields with measurable orientation and strength, which can then interact with other magnetic elements to produce mechanical work. The relationship between electric current and magnetism also forms the basis for electromagnetism as a whole. Maxwell's equations, which describe the behavior of electric and magnetic fields, are built upon the principle that moving charges create magnetic fields. Rowland's experiments provided one of the earliest direct confirmations of this principle, offering empirical support for the theoretical framework that would eventually describe electromagnetic waves, light, and a vast array of modern technologies. By establishing the direct connection between current and magnetism, he helped bridge the gap between abstract theory and tangible observation. Moreover, the connection between moving charges and magnetism is not confined to engineered systems. It is a fundamental aspect of nature itself. Planetary magnetic fields, for example, are generated by the motion of charged particles in molten cores, creating geomagnetic fields that guide compasses and protect life from cosmic radiation. Stellar magnetic fields, including the Sun's, arise from the movement of ionized plasma, generating solar winds and magnetic storms. Understanding that motion of charge produces magnetism allows scientists to analyze these large-scale natural phenomena using the same principles that govern Rowland's laboratory experiments. Demonstrating the universality of the concept, Rowland's experiments also illustrate the subtlety of the relationship between current and magnetism. While moving charges produce magnetic fields, the magnitude of the effect depends on numerous factors: the speed of the charges, the density of charge, the geometry of their path, and their interactions with surrounding materials. By carefully controlling these variables in his experimental setup, Rowland was able to isolate the magnetic contribution of moving charges and distinguish it from extraneous influences. This attention to detail emphasizes that understanding the connection between current and magnetism requires both theoretical insight and meticulous experimentation, a lesson that continues to guide research in modern electromagnetism. The significance of this connection extends to modern technology in profound ways. Magnetic resonance imaging, for instance, relies on the interaction between magnetic fields generated by moving charges and atomic nuclei. Data storage in computers uses the magnetic properties induced by controlled currents in microscopic domains. Communication technologies, from radio waves to fiber optics, exploit the principles of electromagnetism, all of which are rooted in the fundamental relationship between moving charges and the magnetic fields they generate. Rowland's work, by providing experimental evidence of this relationship, laid the foundation for these technological applications, bridging abstract physical principles and practical utility. In addition, the experiments highlight the importance of visualization and conceptual models in understanding complex phenomena. By demonstrating that moving charges generate magnetic fields in a reproducible and measurable way, Rowland allowed scientists to develop mental and mathematical models of electromagnetism. These models enable prediction, manipulation, and innovation, turning abstract laws into actionable knowledge. The ability to conceptualize magnetic fields as arising from currents transforms them from invisible, mysterious forces into tangible, predictable effects that can be harnessed in myriad ways. Rowland's work also emphasizes the interconnectedness of physical phenomena. The fact that moving charges generate magnetism implies that electrical and magnetic forces are not separate entities, but manifestations of the same underlying reality. This insight underlies the unification of electricity and magnetism into the single framework of electromagnetism, which later provided the foundation for the theory of relativity and modern field theory. The laboratory observation of moving charges producing magnetic fields is thus a microcosm of the broader principle that seemingly distinct forces may be linked through fundamental interactions, a principle that resonates throughout the history of physics. Finally, the connection between electric current, moving charges, and magnetism underscores the predictive power of scientific inquiry. Once the principle is understood, it allows scientists to anticipate the behavior of systems ranging from simple circuits to complex plasma flows. It provides a reliable framework for experimentation, measurement, and technological design. Rowland's experiments demonstrated this principle empirically, confirming that the predictions of theory correspond to the behavior of the physical world. This convergence of theory and experiment is one of the hallmarks of robust scientific understanding, and it is precisely what makes the connection between current and magnetism so foundational. In conclusion, the connection between electric current, moving charges, and magnetism is central to our understanding of the natural world. Rowland's experiments provided concrete evidence of this connection, demonstrating that the motion of charges produces magnetic fields whose strength and orientation can be measured, predicted, and manipulated. This principle underlies both fundamental theories in physics and countless technological applications. It bridges microscopic and macroscopic phenomena, unites abstract theory with observable reality, and provides a framework for innovation and discovery. The elegant simplicity of the principle moving charges create magnetic effects belies its profound significance, and Rowland's work stands as a testament to the power of careful experimentation, meticulous observation, and the enduring quest to understand the invisible forces that shape our universe. The modern implications of Rowland's experiment extend far beyond the confines of his 19th century laboratory, resonating through both the theoretical foundations of physics and the practical technologies that define contemporary life. By demonstrating that moving electric charges generate magnetic fields, Rowland provided an experimental cornerstone for the field of electromagnetism, a framework that underlies virtually every aspect of modern science and engineering. The reach of this insight is staggering. From the smallest particles in quantum experiments to the vast networks of electricity and communication infrastructure that power our cities, consequences of his work continue to unfold. One of the most immediate implications is in the field of electrical engineering. Electric motors, generators, and transformers, which are now ubiquitous, operate on principles that can be directly traced back to the connection between moving charges and magnetism. In an electric motor, for instance, a current is passed through a coil of wire, creating a magnetic field. This field interacts with external magnets or other current, carrying elements to produce motion. Without the understanding that current generates a magnetic field, a concept Rowland verified experimentally, the design and operation of these devices would have been impossible. Modern machinery, transportation systems, and household appliances all depend on this principle, demonstrating how a fundamental scientific observation can ripple outward to transform daily life. The implications of Rowland's work also extend to the field of energy generation. Power plants, whether they use fossil fuels, nuclear energy, or renewable sources like wind and hydro, rely on the interaction between moving charges and magnetic fields to convert mechanical energy into electrical energy. In a generator, mechanical rotation causes charges in a conductor to move, producing a magnetic field and, consequently, an electric current. The precision and predictability of this process, which make large-scale electricity production feasible, rest on the foundational understanding established through Rowland's experiments. By showing that moving charges create measurable magnetic effects, he helped pave the way for the generation and distribution of electrical power on a scale that sustains modern civilization. Beyond classical electrical devices, Rowland's findings also resonate in the realm of modern communication technologies. Radio, television, and cellular communication rely on electromagnetic waves, which are disturbances in electric and magnetic fields that propagate through space. The theoretical framework for these waves, described by Maxwell's equations, depends on the principle that moving charges generate magnetic fields, which in turn interact with electric fields to create self-propagating waves. Rowland's experimental verification of moving charges producing magnetism provided tangible confirmation of this principle, laying a foundation for the technologies that allow instant communication across the globe. The simple observation in his laboratory that motion of charge produces magnetism ultimately underpins the infrastructure of the modern information age. Another profound implication lies in the field of medical technology. Magnetic resonance imaging, or MRI, is a direct application of the principles established by Rowland. In MRI machines, electric currents are used to generate magnetic fields, which then interact with the nuclei of atoms in the human body. The resulting responses are measured and used to construct detailed images of internal structures. The ability to manipulate magnetic fields through controlled currents, a concept verified by Rowland's work, is essential for this technology. His experiments transformed an abstract scientific insight into a tool that saves lives, illustrating the unpredictable yet transformative impact of fundamental research on society. Rowland's experiment also has implications in the study of particle physics and quantum mechanics. At the subatomic level, electrons and other charged particles produce magnetic fields as they move. Understanding these interactions is crucial for the operation of particle accelerators, synchrotrons, and other research instruments that probe the fundamental structure of matter. The predictable relationship between charge motion and magnetism allows scientists to design experiments, control particle trajectories, and analyze the behavior of matter under extreme conditions. Without the foundational understanding that Rowland provided, much of modern experimental physics would be impossible. In addition to technological applications, the modern significance of Rowland's work lies in its conceptual contribution to the unification of physical laws. By demonstrating that magnetism arises from the motion of charges, he helped solidify the idea that electric and magnetic phenomena are not separate forces, but interconnected aspects of a single field. This unification has profound implications for theoretical physics, influencing the development of field theory, quantum electrodynamics, and even aspects of modern cosmology. The concept that motion and interaction are central to the behavior of forces has become a guiding principle in the search for a deeper understanding of the universe. Rowland's experiment also underscores the importance of experimental verification in advancing science. In modern physics, theoretical models are often highly abstract, involving complex mathematics and predictions about phenomena that are not immediately observable. Rowland's work provides a template for how careful experimentation can bridge the gap between theory and observation. By precisely measuring the magnetic effects of moving charges, he demonstrated that predictions could be tested and verified in tangible ways. This approach remains central to scientific methodology today, guiding research across disciplines from condensed matter physics to astrophysics. The implications of Rowland's work are further evident in emerging technologies. Spintronics, for instance, is a field that exploits the intrinsic magnetic properties of electrons, in addition to their charge, to develop faster and more efficient electronic devices. The ability to manipulate magnetic fields through controlled motion of electrons is a direct extension of the principle established by Rowland. Quantum computing, too, relies on precise control of charged particles and their associated magnetic interactions to encode and process information. In this sense, the fundamental insight that moving charges generate magnetism is not just historically important. It is actively shaping the cutting edge of technology and research. Rowland's experiment also informs our understanding of natural phenomena on a planetary and cosmic scale. The Earth's magnetic field, generated by the motion of molten iron in its core, relies on the same principles observed in his laboratory. Stellar magnetic fields, solar flares, and auroras are all consequences of moving charges generating magnetic effects. By establishing the fundamental link between charge motion and magnetism, Rowland provided a framework for interpreting these large-scale phenomena, demonstrating that the principles observed in a controlled experiment have universal applicability. In the realm of education and scientific communication, Rowland's work continues to serve as a powerful example, demonstrating that moving charges generate magnetic fields, provides students and researchers with a tangible, reproducible illustration of abstract principles. It bridges the gap between theoretical mathematics and observable reality, making the laws of physics accessible and intuitive. Modern laboratories, teaching tools, and simulation software all build upon the fundamental understanding that emerged from his experiments, highlighting the enduring educational value of his contributions. Furthermore, the experiment highlights the interplay between curiosity-driven research and societal impact. Rowland did not set out to revolutionize technology. He sought to understand a fundamental question about nature. Yet his meticulous work laid the foundation for countless applications that define the modern world. This trajectory from basic research to transformative technology underscores a recurring theme in science. Fundamental discoveries, even those pursued for their own sake, often yield consequences that extend far beyond their original scope. The ripple effects of Rowland's work can also be seen in the integration of physics with other scientific disciplines. Chemistry, materials science, and biology all rely on principles of electromagnetism to explain molecular interactions, chemical bonding, and biological processes such as nerve conduction. The ability to understand and manipulate magnetic fields through moving charges allows scientists to probe matter at increasingly fine scales, enabling breakthroughs in nanotechnology, molecular imaging, and drug design. The fundamental insight that Rowland confirmed in a spinning disk experiment now informs research that spans from the atomic to the organismal level. In addition, the principles established by Rowland are central to the ongoing exploration of space and astrophysics. Satellites, spacecraft, and space telescopes often rely on precise manipulation of electric currents and magnetic fields for propulsion, orientation, and measurement. Understanding how moving charges generate magnetic fields allows engineers to design instruments that operate reliably in the harsh environment of space. Cosmic phenomena, from the behavior of charged particles in planetary magnetospheres to the dynamics of plasma in interstellar space, are interpreted using the same principles observed in Rowland's laboratory, demonstrating the universal relevance of his work. Finally, the modern implications of Rowland's experiment are philosophical as well as practical. By revealing that magnetism arises from motion, his work emphasizes the interconnectedness of natural phenomena, the predictability of physical laws, and the ability of careful observation to uncover hidden truths. It illustrates how a seemingly simple experiment can illuminate profound aspects of reality, linking the microscopic motion of charges to the grand-scale structures of technology, nature, and the universe itself. The experiment embodies the essence of scientific inquiry, curiosity, precision, and the relentless pursuit of understanding, with consequences that extend far beyond the laboratory.